Okay, so in the previous videos, okay, we have discussed the application of double integral, okay, by finding the area as well as the volume of the solid. Okay, so in this video, I would like to explain more on the physical application, okay, including mass, center of mass, a moment of mass, and as well as the moment of inertia. Okay, so let's see on the definition first. Okay, so for example, if we consider a flat object, okay, because we are now talking about the application of double integral, okay, so we are supposed to have a flat object, okay, that we call as a lamina. Okay, so it's supposed, or it can be viewed as a two-dimensional solid. Okay, so when we talk about lamina, okay, so I would say that if we have like this, so we can just say that it's gonna be a flat object like this. Okay, so that is by definitions of lamina. Okay, so if we have, okay, for example, if we have a density, okay, a density by definition is a mass per unit area. Okay, so with the density, okay, you can figure out the mass of a lamina. Okay, so by definition, okay, if a lamina with a continuous density function given by delta over here, okay, on the region on xy plane, like what I sketched over here, okay, its total mass, which use a symbol m over here, is defined by the integral of density like this, okay, given by this one. Okay, so this is what we call as total mass, okay, for a lamina over here. Okay, so by right, you will be able to get the mass of a lamina, okay, whenever you have a continuous density function as well as the thin flat like this, which means that you need to figure out the limit, like what you have figure out or learn in double integral. Okay, so the other application that also involve, okay, which is the next one, is the moment of the mass. Okay, so moment of the mass is actually by definition tendency of a mass to produce a rotation about a point, line, or a plane. Okay, it's gonna be can be a positive or negative moment. Okay, so we are talking about the supposed to be the direction, okay, for that rotation. However, we are not focusing on the direction. We are focusing on how can we find the moment of the mass. Okay, so by definition, okay, the moment of the mass about the x and y axis are given by this one. Okay, so once we figure out the moment of the mass, okay, so the next application that we can get it is actually the center of the mass. Okay, so in order for you to get the center of mass, you must be able to get the moment of mass first, because the component of the center of the mass is related to the moment of the mass that we calculate. Okay, and the mass is calculated by using the formula that we introduce in order for us to get the mass, which is by this definition. Okay, so all the applications, okay, related to each other actually. Okay, so the interpretation of this center of mass, okay, we could say that this lamina, okay, so balance, okay, so for example, if we have lamina like this, okay, and then this center, okay, so this center of mass, okay, we can see that this lamina balance horizontally when supported at its center of mass. Okay, so that is the physical interpretation. However, our focus is just to figure out, okay, the center of the mass. Okay, so whenever we have a constant, or whenever we have in a situation that the density is a constant, okay, or we can simply say that the density is equal to 1, okay, to make it easy for us to calculate it. Okay, so the center of the mass that you figure out is called as centroid of the region. Okay, so by this definition, okay, whenever the question asks you to find the centroid, okay, you must know that the density is a constant, so obviously that the density will not be given. Okay, and the last one, Okay, and the last one, okay, the moments of inertia. Okay, so the moments of inertia, okay, also called as the second moment by definitions over here. Okay, so it has been interpreted, okay, by using Ix over here. Okay, so this is, okay, the moments of inertia about x axis for this one. This one is about y axis, and the last one is not supposed to be Iz over here. Okay, it's supposed to be IO. Okay, so IO is called as polar moment. Polar moment of inertia actually. Yeah, because lamina is on xy plane, right? Okay, so but the rest of the, the application of a double integral would be just on how can you apply the formula in getting that one. We are not explain uh, what I'm supposed to say. We are not asked the student to discuss what will be the values that you got in terms of how can you interpret all the values that you calculate. Okay, our main focus is actually to apply, okay, the knowledge on the double integral that you have learned previously, okay, in order for us to find the application. Okay, for example, to get center of mass and everything. Okay, so let's see on the example that I put in my teaching videos. Okay, so we have, okay, so we have a lamina, okay, with density given by this one. So our density right now is given by x square. Okay, so occupies a region bounded by the parabola and the line y equal to x. Okay, so first thing first, okay, it's gonna be the same as what we have learned so far. Okay, you need to get the bounded region. Okay, so if we try to sketch it in 2D, so parabola y equal to 2 minus x square is given by like this, right? Okay, so this one is y equal to 2x square. Okay, and then we have one more, which is the line y equal to x. Okay, like this. Okay, so we are talking about the bounded region, right? So the bounded region, okay, bounded by this line and y equal to x will give you this shaded region. Okay, so if we figure out this one, okay, so we should be able to get the point of intersection over here is supposed to be 1, and over here the point of intersection supposed to be -2 over here. Why the intersection point here is 2. You have y and x over here. Okay, so it's important for you to identify the shaded region over here so that you'll be able to get the correct limit. Okay, so for the first one, okay, the question asks you to find the mass or total mass. So total mass, okay, by definition, okay, is equal to this one, dA. So dA now, okay, it could be dy dx or dx dy. Okay, so this one, okay, it will be easy for you to solve it using Cartesian instead of polar. Okay, but then if in any situation that you have a circular type shape, okay, you can apply a polar coordinate. Okay, so for this one, since we have figured out the density is given, right, we have x square. Say for example, our order of integration that we choose, in this case we choose dy dx. Okay, so in finding the limit should be the same as what we have discussed previously. So based on this one, if I choose this order of the integration, you're going to get that the limit will be -2 up to 1 for x, and the limit for y is supposed to be between x up to 2 minus x square, 2 minus x square over here. Okay, so if you solve this one, okay, so you're going to get that the mass that you figure out from this bounded region, I would say, is equal to 63 over 20. Okay, so the additional parts, okay, when we talk about the applications, actually you need to know, okay, how can you find the mass. Okay, you need to find you need to have the density. So density is given. Okay, so the next one is for you to figure out the limit based on the bounded region. Okay, so that's how we find or solve for mass. Okay, so the next one, okay, the question asks you to find the center of the mass of the lamina. Okay, so we have figured out the mass, right? Okay, based on definition for the center of the mass. Okay, you need to have the moment of mass first, which is the big M and the big M for both. Okay, moment of mass about the X and Y axis. Okay, so we're gonna apply. Okay, we're gonna apply. Okay, using the same shaded region. Okay, since we are talking about the same question. Okay, it's just that now, in order for us to get X bar and Y bar, okay, we need to find my over mass, mx over mass over here. So we have solved for this part, right? The m. Okay, so our intention now is to get my and mx over here, which is the moment of mass. Okay, the first one, mx now. Okay, so mx by definition is given by y multiply with the density. Okay, go to x square. So our dA now, we're going to apply the same order, which is dy dx is going to be the same limit as well, -2 up to 1. So for this one is x up to 2 minus x square over here. Okay, so if you solve for this one, you're going to get that the answers would be -9/7. Okay, so we're going to repeat the same procedure, but now the next one is for us to find the moment of mass about the y-axis. Okay, still maintain the same limit. It's just that now it's going to be x multiplied with a density, which is x square, right? So we have dy dx as well. The same limit, x up to 2 minus x square over here. So if you solve for this part, it's going to get -18/5. Okay, so you have figured out, the moment of mass about x and y axis. Okay, so since we have figured out the mass as well, okay, so now it's going to be the final step, okay, in order for us to get the center of mass. Okay, the center of mass that we are looking for is actually the x bar. Okay, so the x bar is given by, okay, my divided by m. Okay, so my that we calculate just now is -18/5 divided by the mass that we calculate in part A is equal to 63/20. So if you solve for this part, you're gonna get that this one is -8/7. Okay, so the next one is y bar is equal to mx over total mass. So over here we're gonna get that -9/7 divided by the mass, total mass is gonna be -20/49. Okay, so the final answer, the center of the mass that we are looking for is equal to -8/7, -20/49. It's supposed to be right in coordinate because we are talking about center of the mass, right? Okay, so that's how we solve if the question, okay, is about the application of double integral. Okay, no matter what kind of application that we assess, okay, during exam or any kind of question, okay, as long as you have a prior knowledge on double integral, it should be no problem for you to solve it. Okay, so I did provide this exercise that you can try by yourself. Until next video, thank you.